Hello, I'm Andy Backhouse from Outokumpu Stainless in Sheffield. I'm pleased to present this paper on recent developments of stainless steels in structural applications, written together with Nancy Baddoo from the Steel Construction Institute in the UK. The Steel Construction Institute are a technology institute focusing on applied research and development of steel structures, with stainless steel's one focus area, and my own company, Outokumpu Stainless, is the largest producer of stainless steels in Europe. So this virtual event is organised from Sheffield, which is the home of stainless steel, first produced here over 100 years ago, although many of the grades used in structural applications have actually been developed in the last 10 to 20 years and are therefore quite modern materials. In fact, many were only introduced into the Eurocode in 2015. There is a particular subset of stainless steel grades known as the Duplex family that have become the main stainless steels used for structural applications, and the reason for this is that they all have the high corrosion resistance associated with stainless steel, but an important advantage of a high yield strength of around 450 to 550 megapascals, and this without any significant extra cost compared with the more common stainless steels such as 316L EN 1.4404. And this, of course, has allowed engineers to design lighter weight structures, which has multiple benefits of reducing the quantity of materials, thus reducing materials and fabrication cost. It's allowed more slender and aesthetically pleasing structures and lower materials usage, which reduces the embodied carbon. This is, of course, becoming increasingly important in today's world. The contribution of the academic community so far has been fantastic. They've led to a good set of design rules, and these are in the process of being thoroughly updated in the major revision of the Eurocodes. Fabrication techniques are now widely used and understood, and together all of these aspects has resulted in a growing number of structural engineering projects that have made structural use of stainless steel. One particular area of application is in bridges, and over the last 20 years there have been quite a few pedestrian bridges built from stainless steel, largely with aesthetic intent, but what I decided to show in the presentation is a few examples of bridge structures using stainless steel that have been introduced for more utilitarian functional uses. The first example is from the Swedish capital Stockholm, where the main railway line from the south of Sweden into Stockholm Central Station bridges over a 180-metre long stretch of the Baltic Sea. The photo on the right is a view from several years ago of a carbon steel structure showing the outermost girder of this superstructure. It was built in the late 1950s, but by the 2010s had become heavily corroded and needed replacement. So a costing study was undertaken by the Swedish Transport Administration, and this showed that the maintenance cost of replacing with painted carbon steel would be very high, mainly due to difficulties of access. And the extra initial cost of using a more durable material such as stainless steel was worthwhile. Actually, for painted carbon steel, the first major maintenance event was calculated to cost about 30 million euros, which completely dwarfs the extra cost of using stainless steel in the first place. And when you add to that the future disruption to passengers of maintenance closures and the need for maintenance workers to work in a dangerous railway environment, it altogether gave a clear answer to replace the entire structure with a very low maintenance duplex stainless steel structure. So here we see on the left the old corroded superstructure in carbon steel. There are actually 4 similar lengths, parallel sets of plate girders, all with transverse bracing. On the right hand side is the final site installation steps of a new fully welded duplex stainless steel structure. Most of the fabrication took place in a workshop. 12-metre long sections were delivered to site by barge, craned into place and welded together on site, as you can see, and the total project used about 600 tonnes of duplex steel. The view on the right is one of the last times anyone will see this structure, because now the trains and the tracks sit on top of this superstructure, and the intention is that a 120-year design life will be achieved without any need for any significant maintenance interventions. As well as pedestrian and rail bridges, there are also examples of road bridges with duplex steel structures. This is Pooley Bridge in the Lake District in the northwest of England. This is a bridge installed last year, after the previous old stone bridge was washed away in floods in 2015. And in this case, the Duplex stainless structure acts compositely with a concrete deck. There are duplex studs connecting to the concrete, and it's also a duplex balustrade. And the studs were produced using offcuts from the plate and fillet welded to the main steel structure. Stainless here has several benefits. First of all, it's a road inside a national park, so long-term aesthetics are certainly important. And although the rural environment is quite benign, it's in a part of England that does expect freezing winter temperatures and snowfall, so the steel benefits from its corrosion resistance to the road salt used for de-icing. The open design and the material are such that in future storms water can pass freely under the bridge, and the material is itself quite resistant to any damage from floodwater debris. Whilst the design followed the principles of the Eurocode, there is a relevance here for future research work, in that there is a general lack of comprehensive data on stainless steel working compositely with concrete, and in particular there's a need for greater understanding of the performance of stainless shear connectors. And with more data, it would be possible to improve design rules to further optimise material usage. And this will be especially useful for functional composite bridges, using more utilitarian plate girders in stainless steel, acting compositely with concrete decks. So flooding has been a topic in recent months in Central Europe, and it's a problem that besets many parts of the world, and duplex stainless steel is quite often being used in this type of setting, since it's quite resistant to the abrasive effects of sand and the corrosive effects of salt water and even fresh water. This example is in New York. This is South Ferry Station, part of the New York City subway in Lower Manhattan, where in 2012 Hurricane Sandy led to extensive flooding of the subway station with salt water and sewage. And actually the station had been refurbished only 2 years previously. It was flooded from the tracks to the mezzanine, and all of the electrical and mechanical systems were destroyed. So in order to repair the station once more and ensure it wasn't flooded again, these new surface entrance structures were installed. These are made from duplex stainless steel, channels and eye sections, and ensure the entrance can now be completely sealed off to prevent the ingress of floodwaters. And of course, stainless steel used for the high strength and resistance to emergency events such as flooding. A final example is a demonstration of wider thinking of use of engineering materials and stainless steels and how they can impact on the environment and the circular economy. Of course, carbon footprint is becoming a topic increasingly on the agenda of structural engineers, and stainless steel starts with having quite good credentials in this regard, in that it is fully recyclable by remelting to produce new steel. But actually we think there are even greater benefits that can be achieved, not only by making long life structures, but by making structures that are flexible and adaptable to change, so that greater value is extracted from existing materials. So this is a simple, quite functional pedestrian bridge over the main highway near the town of Södertälje in southern Sweden. It's an example of several similar bridges designed with the same basic design being used in other locations. It's a fully duplex stainless steel structure, and what the rather nice thing here is that it is a modular design with sections bolted together. So the bridge, of course, has the potential to last for decades without maintenance. No need to close the road for future maintenance, but in future, perhaps in a few decades' time, this bridge might need to be changed and reconfigured. Perhaps the road might need to be widened and a longer span needed. Perhaps it will be decided that the bridge is no longer needed at all here. In either case, it's no problem. The bridge owner has got options. Either new modular sections can be bolted on to increase the span, or else if the bridge is not needed, the entire bridge can be dismantled and reused elsewhere. And stainless steel has been used here because it's well placed to be reused, as its high durability lends itself to this type of repeated handling, and even relocating the structure in a new area, the bridge will still be in good as new condition. However, for this concept to be more widely applied to structural components in bridges and buildings and the like, more research is certainly needed to develop better rules to allow flexible reuse and recertification. application of structures. And there are many more opportunities for studies that marry together thinking of how best to achieve a circular economy together with using long life stainless steels. The service life of bridges is often only 100 years, but there are areas where research could facilitate better reuse without need to recycle. So one example in a composite bridge could be the development of demountable and reusable stainless studs. And in other areas, sometimes the service life of a particular application is not limited by the stainless steel, but by other aspects of an application. And here I'll show a non-built environment example. This is a structure, but it's a structure of a bus. And stainless steel is often used in structural frames for buses. Stainless steel has very nice energy absorbing properties and a suitably long life expectancy. But a bus might only be used for 15 to 20 years, and the stainless steel will last for much longer than that. So what is needed are strategies for reuse of the structure rather than just remelting and recycling the steel. So I think these are challenges that the academic community is well placed to challenge the status quo and propose holistic solutions to these problems. Another area that needs more research is in structural efficiency. Efficiency has a dual impact with stainless steel. Of course, we're talking about reducing the amount of material used. It's good for carbon footprint. But with stainless steel, there's a second important aspect in that minimizing materials means greatly minimizing the financial cost too. So we need more tests on stainless steel eye sections. The database of tests is relatively small, so at the moment design recommendations are quite conservative. And there are lots of opportunities for improving data on asymmetrical eye sections, perhaps with one flange wider or thicker than the other, perhaps one flange with a different grade, and all these have opportunities for improving material usage. Connections need to be much better understood. There's a lot of work that's needed to generate data on bolted and welded connections, again to develop less conservative design rules. And overall, this is focusing on weight reduction. This is really important at reducing cost and carbon footprint. And one aspect we're involved with, the pictures on the right are photos of a current project that we are part of together with Chalmers University and several other bridge designers and fabricators in a consortium where we're looking at corrugated webs for girders, which is targeted at weight reduction and cost reduction, as well as carbon footprint reduction. So in summary, there's a wide growth of duplex stainless steels for a broad range of reasons, spanning economic, environmental, durability and aesthetic reasons. But there's a large untapped potential, and we certainly need the support of the academic community to look and really exploit these wonderful materials in the future. Thanks for listening.